Hey everyone, so in this video we're going to tackle a problem involving a Venturi meter. We're given two readings of pressure and also the diameter of the circular pipe. We need to solve this for the mass flow rate inside the Venturi meter. So to solve this problem we're going to use two equations. The first one is Bernoulli's law, which applies on a streamline. So a streamline is just the series of positions that a particle will take. And so you can say we're going to take it here. This is point A, and this is point B. So yeah, right before we get to it, we're also going to use the continuity equation, which simply states that the mass flow rate is equal at every position within the Venturi meter. If not, then there would be accumulation of mass in some area, and so that does not happen. All right, so often with Bernoulli's law, what we can do is simplify. And the way that we simplify is that, well, let's say here, there's no change in height. So if, let's say, we bring the gz sub b term to the left, we will get gz sub a minus z sub b plus va. We're also going to bring the velocity term to the left, so we'll get va squared minus vb squared over 2 plus pressure at A divided by the density of water is equal to pressure at B divided by the density of water. I just forgot to put the density symbol there. Okay. So yeah, let's do that. This is equal to 0 because delta, let's say, height is 0. So we can isolate, or rather say that, oops, VA squared minus VB squared is equal to 2 times P sub B. So that's 150 times 10 to the third power minus 200 minus 200 times 10 to the 3 divided by the density of water, which is 1,000 kilograms per cubic meter. Okay, so we can rearrange that to, this is going to be negative because we have 150 minus 200, so we're just going to flip VB squared minus VA squared. And so we're going to take the negative value of this, which is simply 150 minus 200 is minus 50 times 2 is 100. 1,000 divided by 1,000, so it's just 100. Yeah. Okay. So the other thing we're going to do is we're going to take the continuity equation and we're going to rewrite it in terms of density, velocity, and cross-sectional area. Well, that's just density times velocity times area, density, velocity at B, area at B. And so the density terms cancel out, The velocities, we do not know them, but they're unknown in the other equation 1 that we have here. So let's say velocity at A is equal to cross-sectional area B divided by cross-sectional area A times velocity at B, and we can actually calculate that. So we're going to have pi over 4 terms, which are going to cancel out. Still write them, but divided by diameter squared, so d sub b is 0.1 divided by 0.3 squared, and all of that multiplied by VB. Okay, so VA is actually equal to 1 over 9 times VB, and we'll just have to live with that. 1 over 9, so that's 0.11. Let's keep 3 decimals, VB. Okay, so we have this partial result and this partial result. So if we substitute, we will get VB squared minus 0.111 VB squared is equal to 100, and that will give you VB value of 10.06 meters per second. And so we only need one velocity term. You don't need the other one, because you just need to use one mass flow rate. So the density of water times the velocity at B times the area of the cross section at B. So the mass flow rate at A is equal to the mass flow rate at B is equal to the density of water times the velocity at B cross-sectional area at B. So that's 1000 times 10.06 times pi over 4, and we said that at B we have a diameter of 0.1 meters, 0.1 squared. So the mass flow rate is equal to 79 kilograms per second. I'm just going to double check this. Yeah, okay. Yeah, I went full OCD with the pi term, but anyway, so yeah, that's the answer. All right, so typically when you have a Venturi meter problem, you just need to use some combination of Bernoulli's law and the continuity equation. Don't forget, you can make some simplifications. Sometimes the pressure at A is going to be the pressure at B when they're both equal to the atmospheric pressure, so you can sometimes simplify those. And that's it. So thanks for watching.